Hello, today's topic is arc length. We'll also have a little look at surface area later, but we'll focus mostly on the arc length. And in particular, how do we find the length of some sort of curve from a function? Okay, so let's take some typical function. Okay, so this can be anything. If you're paying close attention, you may have realized it's probably sine x, but it's just representing some generic function. How are we going to find the length of this? Okay, it's not straight. It's not a circle in any way, we know how to work with that, but this is just some sort of curved function. Okay, so the first thing we can do, we can start breaking it up into pieces. And of course, for those who've been doing calculus for a long time, we're very familiar with doing this. So we've broken this up into 4 pieces now. They're 4 equally width pieces, but obviously they have different lengths. And because those are straight lines, we could find the length of each of those. And if we break it up one further, so now we have, I guess, 6 pieces. Again, we could find the length of each of those straight lines and add them together to get an approximation for the length of the curve. And hopefully, as you can see, as we add more, the estimate we'll get would be better for the length of the curve, the arc. Okay, so well, how do we do this? How do we find the length of the straight lines? In this case, the red line. Okay, the approximation for the blue line we have there. Okay, well, we're looking for the length of that red line. We know by the Pythagorean theorem, we can take the delta xi and the delta yi to be the two sides of the triangle, and the red line, the length we want, would be the hypotenuse of that. So we could square each of those, add them together and take the square root, and that would give us the length of the red line, and that would be our approximation for the length of the blue line. And of course, as we take more and more of these little broken up pieces, the more accurate our estimate becomes. Okay, so let's find a formula. We'll just put the diagram in here to help us see a little bit what we're doing. And say, because we're using the Pythagorean theorem, we have the square root of delta xi squared plus the delta yi squared. Okay, that's going to give an approximation for the length of the arc, the curve. Okay, well, we'll use a little bit of algebra on this to make it simpler to use. Okay, we factor out the delta xi squared. Of course, we're left with just a 1 here, and we get a delta yi squared divided by a delta xi squared here. And then, in fact, we can take that delta xi outside the square root because it's squared, we get the square root. And so we're left with this, and then this is the piece we're interested in, the delta yi squared of the delta xi squared. Okay, and well, we think about that. Delta yi over delta xi is going to be kind of a rise over run. Okay, changing y over changing x, and it'll be all squared. And in fact, we can approximate that by the derivative. Okay, we take the derivative of the function at some point, in this case c, that will be given by the delta yi over the delta xi. Now, of course, it's squared because each term is squared. And so we're left with this. We get the square root of 1 plus f prime of ci squared delta xi. And now we're back to doing what we've done many times. We take the limit as n approaches infinity of this sum. That gives us the most accurate, in fact, the perfect estimate. By taking the limit of that sum, and we have the delta xi's outside, we get the actual formula for the arc length, which will be the integral from a to b. Okay, we haven't actually seen the a and b, but they're just from what values the function goes from and to in the x direction. So it goes from a to b, and it's a square root of 1 plus f prime of x squared. So we differentiate then square, and that's integrated with respect to x. So we have the dx. Okay, so there was a bit of algebra going on there, but the actual formula we've ended up with is not too bad, and in fact here it is in its nice box. So assuming that our function is differentiable, of course we have to have it to be differentiable, so we can do this on the open interval between a and b. And we're also going to assume that that derivative is continuous on a to b. Then the arc length of the function is given by this formula. Okay, so probably time we saw an example. So here's an example, maybe we'll just throw the formula in here. Okay, so we want the arc length of 4x plus 2 to the power 3 over 2, and it's just going to vary from x equals 1 to 2. Okay, so it's a sort of a couple of step process this to find it. Well, first we'll find the function, and we'll find the derivative of the function. Okay, remember the derivative's in the formula there. So we take the derivative, then we need to square that, which in this case, of course, it's been nicely set up so that it squares quite nicely. In fact, if we square the derivative there, the 6 squares to 36, and of course we have the x plus 2 to the 1/2, so we square that, we just get x plus 2. And now we can plug that into the formula we had. Remember, it's 1 plus f prime squared, and we get this. And so finally we're at the stage where we can just integrate, where we can perform the integral. It's not an easy integral, but it's not too bad. A little substitution there. So we get the 1 over 36 outside, we get the 2/3 outside. Remember, dividing by 3/2 is multiplying by 2/3. And that's our integral between 2 and 1, and we plug the values in. And well, at this point, of course, we have to turn to a calculator, but that is the value. That is the arc length of that function from x equals 1 to x equals 2. Okay, so I mentioned at the start, one more little piece we're going to look at is surface area. I'm not going to derive the formula for surface area, we'll just leap straight in. Okay, so we're taking a solid of revolution. Okay, so taking something, revolving it around an axis, either the x-axis or y-axis, or maybe somewhere else. Again, we're going to assume that we have a derivative and that that's continuous on the region. And if that's the case, if we're revolving around the x-axis, the surface area is given by this formula, 2 pi integral from a to b of fx multiplied by the square root of 1 plus f prime of x squared. Whereas if we're revolving around the y-axis, we get, it's actually a very similar formula, it's just slightly different. Revolving around the y-axis, we get 2 pi, then we get the integral from a to b, and then we get x multiplied by this same square root. And the f of x and the x here just really are the radii, depending on which direction we're looking in. Okay, so let's take an example. Find the surface area of the solid formed by revolving y equals 2x from 0 to 1 about the x-axis. Okay, maybe before we actually look at it, we'll have a little look at a picture. Okay, so looking at the picture here, we've got the 2D version. So obviously the function is just y equals 2x. It's a very simple function from 0 to 1. On the right-hand side here, you can see we've also got the function, but then we've got the circle. Okay, this is the circle that will be formed when we revolve this. Remember, we're revolving it around the x-axis. So as we move it along, it's getting revolved around the x-axis. The x-axis is here. And of course, as we get close to the origin, the circle shrinks to nothing. And as we get further away, it gets bigger and bigger. And if we are to put a trace on this, so we can sort of see how it works. Okay, as we fill in the gaps, you can see the shape that's forming is a cone. It's a big wide cone. Okay, so that's the surface area we're looking for. Okay, maybe again we'll just bring in the formula that we'll need. It'll be down there. So we get f of x, and then it's a square root of 1 plus f prime of x squared. Okay, of course we have the 2 pi outside, and we're integrating from 0 to 1. And from this point, actually, this is very straightforward. We differentiate 2x, we just get 2, and then square that, we get 4. So we've got the square root of 1 plus 4, we can take that outside. So we have 2 root 5 pi, then we integrate from 0 to 1 of 2x, and so that just works out to 2 root 5 pi. Okay, and so that is that surface area. Okay, and that's about all for today.